Okay, so here we're going to talk about the motion of a pendulum and prove that for a small angle from the equilibrium position, that pendulum motion is simple harmonic motion. So we start out, we have a pendulum, let's call its length L, and let's assume that the cord itself is massless. So the only mass in this system is really the mass all the way on the end here. So we have two forces acting on this mass. We have gravity pulling it down, and we have the tension up and to the right in this picture. So since this thing is moving in a circular arc, I want to think of it along those lines and think about it in terms of centripetal acceleration and tangential acceleration rather than like in the x direction and in the y direction. So I'm going to split this gravity force into components. I'm going to draw it like this. And if the angle theta here is in this picture, it's going to be the same angle here, which is going to make this mg sine of theta, and it's going to make this mg cosine of theta. Okay, so let's look at the motion in the tangential direction. So Newton's second law says mass times acceleration equals net force. And the only force in the tangential direction is this mg sine theta force. So I'm going to write this way. Now you'll notice that I wrote this with a negative sign. And the reason for that is, if you can imagine, if we start from center, we're rotating in a clockwise way to go from the equilibrium position to where the object is now. But the acceleration is opposite that. So the acceleration is kind of like in a counterclockwise way. So it's the opposite direction, which is why the minus sign. We can divide m on both sides, and we get a tangential is negative g sine theta. So we can see this, but we need to think about it in terms of the angle. So what you can imagine here is that the linear acceleration is related to the angular acceleration. If you think back to our rotation unit, we learned that r times the angular acceleration would equal the linear acceleration. So in this case, L, the length of the pendulum arm, times the angular acceleration would be equal to negative g sine theta. And we know that theta and alpha are obviously related, so that's why we wanted to do this. Alpha is the second derivative of theta with respect to t. So we can rewrite as second derivative of theta with respect to time, like so. If we divide both sides by L, we get this. So if you look at this, this expression is similar, not exactly the same, but similar to our equation for a spring. We had the second derivative of x on one side, and we had a negative fraction on the right-hand side times x. The problem with this is that we have this sign in here. Because that's in there, this is not simple harmonic motion. We don't have an acceleration that is proportional to the displacement. We have an acceleration that's proportional to the sine of the displacement. But here's an interesting point. For small angles, if we look at, let's say, anywhere between 0 and 15 degrees, something like that. Okay, obviously you could put that into radians. Think about the angles in radians there. That would be anywhere from 0 to pi over 12 radians. Here's an interesting fact. For small angles like that in radians, the sine of the angle in radians is approximately equal to the angle itself. You could try this out on your own with a calculator. If you put in, like, let's say, pi over 12. Okay, you can put in pi over 12 and get a number, decimal. And then you can also do the sine of pi over 12, making sure you're in radians. You're going to find that they are very, very close. And the smaller you go, the more close they get. If you did pi over 18 or pi over 20 or 36 or something like that, you'll see they approach each other when the angles are small. So if this is true, then for small angles, we could write this instead. It's approximately equal to negative g over L times theta instead of sine of theta. Now we know that something like this is simple harmonic motion because we've already solved a differential equation like this. What we'll do is we'll substitute, we're going to let omega squared be g over L, and we get negative omega squared theta. And the solution to this differential equation, as we've talked about, theta of t equals a cosine omega t plus phi, phi being the phase angle. This also points out an interesting point. We learned that the period of any object in simple harmonic motion is 2 pi divided by omega. So for a pendulum specifically, we have 2 pi divided by the square root of g over L, which we can rewrite as 2 pi root L over g. So it shows that the longer the length, the longer the period will be, and the higher the acceleration due to gravity, the shorter the pendulum period will be. If you think about that conceptually, it does definitely make sense, and it checks with our, physical reality. If you've been on like a swing set before, you understand that this is the case.